Alrighty, so my name is Phil Zito. I am the founder and CEO of Building Automation Monthly. If you don't know who we are, we provide online training. We've got Building Automation Monthly podcast, YouTube channel, provide free trainings like today. And my background, so I came out of the US military as entered as a technician into BAS, started with Allerton, moved into Johnson. I ran an ops team, I did sales, I did analytics. I actually helped Cree and Molex write their backnet stacks in C#.NET framework. I managed the system integration business at Johnson Controls. Well, I managed the technical integration program at Johnson Controls, which was a subset of the system integration business. So that was a $250 million P&L. During that time, I've created integrations for consuming nurse call data and automating the control of patient rooms during heart attacks, and pulling in flight information system and automating the controls of building automation, lighting, infotainment, things like that within a airport. Done a bunch of different stuff, data centers, list goes on and on. So suffice to say, I've touched almost every system out there and done a ton of programming as part of that. So what we're going to be covering in today's webinar is what is programming. I'm going to talk through that, kind of give philosophy on programming. I promise you that is the only philosophy part of this webinar, but it's an important part because our mindset when we come into programming really dictates whether we're successful or not. Then we're going to talk about points. We're going to talk about the different types of points. We're going to talk about logic blocks and kind of how you can understand them. We're going to talk about real-time versus compiled programming, design patterns. We'll look at some of those. We'll talk about why design patterns are so freaking important. And then we'll look at the programming process, and we will program a simple program. If you haven't already done so, on your handouts, there's an RTU spec. I encourage you to download that, but do not read it until we get to the portion where I tell you to read it, because you won't be paying attention to what I'm teaching you. All right, so what is programming? Well, programming quite simply is the act of taking a sequence, or not even a sequence necessarily, just some sort of use case, some sort of outcome that your customer, your engineer, whoever wants to achieve, and then turning that into logic, whether that is graphical logic, like we'll be talking about today, or whether that is line code, which, some folks like Siemens, Reliable, KMC, Delta, they use line code. Whether it is line code or it is graphical programming, it's taking your knowledge of what they're trying to accomplish and translating that to graphical programming. So how we do that is through a programming environment. And what we're looking at right here is Niagara Workbench. So the reason I teach on Niagara Workbench as well as EasyIO CPT is that, for one, EasyIO CPT is a free software, and they have a virtual machine that runs a virtual controller. So if you can't afford Workbench, it's a no-cost option to practicing programming. The reason I teach on Workbench is because of its market share. Niagara has such a large market share across the world, and especially now that they're pushing the Niagara stack down into the physical controllers, it's becoming even more important to understand it. Now, the thing is, and we'll talk about this in real-time versus compiled programming, how you program in Niagara is a little different than maybe how you program in GFX with Distech, CCT with Johnson Controls, etc., PCT with the UFX folks. So what you have to understand first, whenever you're programming, and this is kind of core of programming, is understanding points and logic blocks. So when it comes to points, we really deal with two types of points, right? We deal with logical points, which exist only in software. These would be things like your set points. These would be like in law network variables, NVs. So logical points exist only in software, and physical points are physical I/O that you are connecting to in the controller. It's really important that you understand the difference between those two, because how you approach programming is going to be based on understanding, am I using a logical point or am I using a physical point? I'm not going to belabor that too much because no one said in the survey that they didn't understand programming, so I don't think I have to go much deeper into logical versus physical points, but if I do, just post it in the questions and I'll circle back to that. All right, where I'm going to spend a good portion of our time though is under the blocks category. So when we think about blocks, right, if I think about how we approach this, with most manufacturers, you will have a set of common blocks that will stretch across everyone's software. And then you will have specific blocks specific to that manufacturer software. So for example, let's talk about a common block, an AND block, right? An AND block is a simple Boolean input, Boolean output block. So when we talk about programming, we're talking about three real data types that we're going to be dealing with: Booleans, integers or numerics, depending on what you want to call them. And those are basically floating points, analog points, right? Analog, meaning that it varies. Whereas Boolean is a true, false, 1, 0 state, analog is a variable state, so it's typically a number. And then enumerations, which are also known as multi-state values, also known as arrays, just depends on your programming software. And so when we look at blocks that are common, that you abso-freaking-lutely need to know, we look at our Boolean blocks. Our Boolean blocks are almost always going to be AND, or, okay, XOR, NOTs, things like that, okay? These are blocks that we absolutely need to understand. Now, we don't have time in this webinar to go through truth tables. Actually, let me click here. My mouse is being a little wonky and that is double clicking for some reason. But we don't have time to go through truth tables. But a truth table basically is, if you have a certain condition of inputs, you will get a certain condition of outputs. So if you're taking notes, which I highly encourage you to do during this webinar, granted, you will get a recording, but I encourage you to take notes regardless. What we're focusing on here, and you know what I did not do at the beginning? I did not go and check that you all can see my screen, but you guys are not saying that, hey, we can't see your screen. So I'm pretty sure you can see my screen. All right. So as I said, Boolean blocks, we really want to know right off the bat. And as I mentioned, I'm not going to have time to go through truth tables, but we've got a blog article about BAS programming. I'll send it all to you after this webinar. All right, so from there, right, we go into things like comparative logic, greater than, less than. These are all things, and this is actually one of the more, so Boolean is probably the most important logic blocks because you use them on almost every program. Immediately followed by comparative blocks. So comparative blocks we're going to use substantially in a lot of our design patterns. Some of the design patterns we'll talk through today. And so it's really important that we understand greater than, less than or equal to, not equal to, et cetera, et cetera. And this double clicking is really obnoxious. All right. So with that being said, those are our basic logic blocks. Now, as we get into some of the more manufacturer-specific logic blocks, we start to look at, in our case with Niagara, we're looking at a library called kit control. And we start to see they have things like lead lag cycles, which is basically for going and cycling chillers and air handler compressors, things like that, whatever you're trying to do on lead lag. Or dual fans, fan walls, etc. Loop points is basically PID loop, and T-stat is a poor man's PID loop that is basically supposed to emulate a temperature control driven PID loop, but I don't personally like it. I prefer loop point. So that is some of the manufacturer specific stuff. So you can start to see how when you get away from Boolean, you get away from comparative logic, and you move into loop logic, sequencing logic, you move into things like latches, you move into things like selects. that is where you start to get more manufacturer specific. Now, this is where a lot of folks get screwed up. They are, oh my gosh, I don't have the switch block, I have the select block or the latch block or etc. Instead of having a flip-flop, I have a latch. And that hoses them and they get frozen, and it's not necessary. So whenever you're dealing with this, and some manufacturers are better than others, I recommend that you, first off, if you're like, I can't figure out what logic block to use. I'm on a job site. I totally get what an AND block is, but I can't figure out these latches. I can't figure out these selects, et cetera, et cetera. What do I do? That's where I highly recommend you utilize the manufacturer's information. Now, like I said, some manufacturers are better than others. So here I'll just show you. So let's say we don't understand what we're supposed to do with the Boolean select. So we would just say Boolean select, type it in search, wait for the search to actually come up, and then we'll see, okay, Boolean select is a Boolean select. It's found in the select folders. See selects for overview, and then we can start going through select. It allows one of multiple inputs to be selected, pass through to the output. So as we start to read select, then we start to realize this is actually more like a mux block than it's like anything else, because this can allow us to have, especially with enum selects. So we start to figure out this kind of, oh, okay, this is what this block is able to do, and then we're able to fit it into design patterns, which, like I said, I'll talk about in just a second. But before I go there, I want to talk about real-time versus compiled programming. So Wiresheet is real-time programming. And this is kind of what's neat about them pushing Niagara to edge controllers. You're also seeing other manufacturers start to push their frameworks using a single programming tool to their edge controllers. Edge controllers just being really a marketing way of saying controllers that are in the field, air handler controllers, VAV controllers, fan coil controllers, etc. And most of us, when we talk about controllers, we're actually dealing with free programmables. Very few of us are dealing with ASCs, application-specific controllers, anymore. We're mainly focused on free programmable controllers, all right? So when we're talking about a real-time programming environment, what that means is, and I don't have a actual edge controller mapped in. If I did, it would be here under our Niagara network, and it would be mapped in, but I don't have one. So what would happen is, with an edge controller that has Niagara framework pushed down, or anybody's framework pushed down, you would be able, and it having real-time programming capabilities, as you went and added things to the Wiresheet, they are automatically in the controller. Now that's different versus compiled programming, where you either have to compile and then download the programming to the controller, or you just have to download the programming to the controller, and the controller has to reset or potentially just update, and then the programming takes effect. So that is the big difference between real-time versus compiled programming. So hopefully that makes sense. I'm giving you all a lot of foundation here that may be basic to you, because I want you to have that foundation as we move into the design patterns and as we move into the programming. So with that being said, do we have any questions so far? Feel free to type them into the question box, and I will start moving through design patterns. And then after that, I'll loop back to any questions. So design patterns. When I started to think about creating our programming course, and I started to think, I'm just going to give you my straight up opinion. I think most manufacturer training is terrible for teaching you how to program. They give you a workbook and they tell you, hey, follow these exact steps, add these exact blocks, and you'll create a program. And then you go in the field and the sequence changes just a little bit and you're not able to implement the program. And that's why in that second poll, most of you said creating a program based on a sequence is the biggest challenge you face, which makes logical sense because that's not what manufacturer training teaches you to do. So as we started to create our programming course and I started to think about that, I was like, how can we teach people to program and piece together programming? And so I started to look at how the IT sector programs. And they use what is called design patterns. So design patterns are essentially patterns that repeat themselves commonly within programming to achieve specific results. So for example, there is a pattern called the analog enable pattern, okay? And what that is, let me shrink all this jazz down here. I got too many things open. So what that is, let's say that you need to go and you need to enable an outdoor air damper, okay? So you have your OAD enable set point, okay? Or you could call it Economizer Enable set point, whatever you want. And then we have our OAT, right? Our outdoor air temp. So we have our physical point and we have our logical point. Now, granted, I know that these are both logical points because I'm not using a program or a controller with actual physical points on it, but just play along with me. Pretend this is a physical outdoor air temp and this is a logical point. We're gonna have to play pretend just a little bit. All right, so we have that, and then we are driving an economizer enable command, right? Econ enable command, okay? Now what's going on here is that we also, right, under our, there we go, our logic. So we will say, okay, and here's how I like to do this, is just read through. This doesn't work on every manufacturer's comparative blocks, but on some it does. So in this case, I like to say, if outdoor air enable set point is greater or less than, just depending on the sequence, usually it's going to be less than. So if the outdoor air temp is less than our outdoor air enable set point, gosh darn, this double clicking is obnoxious, then we will enable our economizer. Now you'll notice we have input 10, input 16. That's just a priority array that's built into these objects. So let me just command this to be, let's say that this is 55 degrees. And let's say that our set point here is going to be 60 degrees. Okay, so we see it's true. Now here's the thing. Okay, that works for our economizer enable. But what that also works for is for a preheat enable. That also works for, as we'll see in this rooftop sequence, we're going to have to enable our heating mode. We're going to have to enable our cooling mode. We're going to have to enable our preheat mode. We're going to have to enable economizer. All this single design pattern right here, this single pattern will be utilized there in rooftop programming. This will be utilized to enable chillers. This will be utilized to enable unit ventilators within a warehouse. So as you start to learn design patterns, you're then able to see sequences and you're able to read a sequence. Like I'll open up our sequence right here and we'll go to economizer and let's look at economizer enable. So economizer enable outside air temp is less than 65 degrees. And we see a couple more variables, but as you see these other variables and you can simply go and copy this design pattern, put it into, so interrupt this one less than, you would copy these less than. So let's do that, right? Let's look at this. Outdoor air is less than 65. So let's actually command our enable set point. Let me unclick that, enable 65, okay. Let's look at our other scenario. Outdoor air temp is less than return air temp, so we'll have to add a physical point called return air temp. We'll call it RAT. In this case, we'll say that return air temp is, let's just set it to 72. Let's copy our less than, okay. Grab this bad boy, and if you want, you can label these less thans. So what we're saying here is return air temp, right? Let's look at this. Outside air temp is less than return air temp, okay. So we've got outdoor air temp is less than return air temp. Okay, you're starting to see how we're piecing this together. Let me control delete that line right there. And the supply fan status is on. So let's go and grab another point. Let's call this a Boolean writable, not a numeric writable, and SF_S. So there we go. And we'll go here and grab our logic and block. Okay, true, true. Set this bad boy to true, just that way this will work. And let's pin some slots. Let's pin a third input here. And let's send it there. So you see, we use the exact same pattern, and that is how we go in a program our Economizer Enable. And naturally, we're going to have the Economizer shall close, and so we could code that as well. But you see how the pattern applies, and we're able to use it. And if I wanted to do a unit ventilator, I could do that. So I don't think I need to beat this horse anymore. I think this makes sense to you. So any questions on that? Feel free to go and type them into the question box. I'd love to answer them. Let's look at another pattern while we're talking about it. A common pattern that we see in VAV boxes, in Economizer Reset, is the PID into PID pattern, okay? So PID, proportional integral derivative loop, although we really in BAS should not be using derivative, is a loop type that allows us to take a controlled variable or process variable, basically a set point, a input, and then drive that to achieve a set point. So what we're going to do here with this pattern is we are going to look, in our case, at CO2. And so let's go and add a couple points, because we're going to be resetting our damper actuator based on CO2. So let's say return air CO2. Okay, and then we'll say our CO2 set point. Okay, and we'll set our set point to, let's just say 800 parts per million. Okay, and so what we can do here is we can have our CO2 and we can have it come in, right? So we'll say, what did I want to set this to? Let's set this to 1,000. Okay, so we'll output here, and I'm not going to set up this PID loop, by the way, just so you know. That is going to come into controlled variable. Set point's going to go into set point, and we're going to make sure our loop is enabled. It's not going to do anything because I don't have the proportional band or the integral band, and I don't have any of that set up. But what's going to happen is this is going to come out to damper command. And it's going to drive our damper command. Now that's all well and good. That's a basic PID loop pattern, right? Very, very basic. Now let's say that we needed to do something where we took zone temp, ZN-T, and we wanted to drive our damper actuator based on a min and max cooling CFM for a VAV box. So once again, and I'll grab right here, I'll grab our CFM flow. Okay. And we will grab two PID loops. So we'll grab here loop point, and I'll call this one ZNT PID. And then this loop point will be CFM PID. Okay, so we'll pin slots, controlled, and we'll pin slots here as well. Boom, boom. And what I'm going to do here is I'm going to say, okay, my zone temp, let's set my zone temp to 78. And then we're going to set my zone set point to 72. Okay, so we go here, controlled variable. All right, 70, 78, 72, my PID loop. And let's say well, we'll just set this real quick. We'll just set this up. Okay, so my proportional constant, let me do the math in my head real quick. 100. So that's going to be 100 is going to be the output, and our range is typically 10 degrees. So we'll put a p-band of 10, and we'll put a integral of 5. Like I said, I'm not going to go into why I'm using these numbers here. We have videos on PID loops and things like that. Okay, so we've got our zone temp PID. Now what we need to do is go into math, grab a reset block. Okay, we're going to call this CFM reset. And we will output this in. Actually, I have to go and pin some slots real quick. Give me 1 second. Okay, and we'll say input low. And I'll set this to 0, okay, and input high will be 100. Okay, and then our CFM low, let's say, is going to be 200, and our CFM high is going to be 1,000. Okay, so we've got all this going, and I'll back up, and I will grab my output, put it into my input, and now I have a CFM calculated cooling set point. That's going to go into my set point, and then my CFM flow is, and we'll just set CFM flow at, we'll put it at like 500. And we'll send this over into our controlled variable. Go here. All right, so I want this to be reverse acting. All right, and I want this 100 divided by 1,000, so it should be 0.1, and integral constant of 5, if I did my math right. And so what's going on here is that I'm going to go and take zone temp, all right, you all seeing this? And zone temp set point. And I am going and saying, hey, I'm not reaching zone temp set point. I'm not dropping my zone temp below set point. So I'm sitting here, right? And because I am above, and it's a direct acting loop. And then I've got my CFM flow, my actual CFM flow in the VAV reading. And I've got my calculated CFM between min and max cooling CFM. And it's coming into my CFM PID, which then, would go to my damper output. So I would just go here, and this would be DMPR-O, damper output. And there we have it. So that is how design patterns work, because now I have this pattern, and I can use this exact same pattern for heating CFM reset. I can use this pattern for calculating CO2, all sorts of stuff. So that's how we look at patterns, and then these patterns, we start to understand what they're trying to achieve. And then when we look at our spec, we're able to say, okay, I know these patterns. I'm able to apply these patterns. And also, if we don't know someone else's programming language, we're able to, excuse me, look at that programming language and identify patterns and figure out what they're doing within that program. All right. So I'm going to take just a second before we move into the programming process and see if anyone has any questions related to anything we've discussed so far. Is this pretty straightforward? Is this stuff you all already knew? Have you guys gotten some ideas out of this? Let me know in the questions box. You can just type it into the questions box. Give me some feedback so I know where you all are at, and then we will continue along with the webinar. All right. So feel free to just type in your questions. I won't be taking any live voice questions in this webinar, but feel free to type them into the questions box. And while you do that, I'm going to have a sip of coffee. All right. Perfect. So let's continue on the programming process. Now, up to this point, we have talked about different logic blocks. We've talked about the different types of programming. We've talked about design patterns at a high level. And now we are going to look at the programming process. So whenever you start programming, if you just start dropping blocks onto a program, it's not going to be as effective as if you had a programming process that you're following. So here's a programming process I use that's worked very well for me. And it is physical, logical, Boolean, analog. So we start off with our physical points. So whenever we're programming, we add our physical points, all of our physical points for whatever we're programming to the programming sheet, to the wire sheet, to the programming logic, whatever you call it. Then we add our logical blocks, all of our set points, all of our calculated set points, things like that. From there, we write our Boolean logic, anything that executes as a Boolean output, so a true, false, on, off output. So that would be things like fan logic, that would be things like enable logic, things like that. And then after all of that, we write our analog logic. And our analog logic are things like PID loops, economizer commands, valve commands, et cetera, set point calculations, things that are analog in their output. So that makes sense? Pretty straightforward? All right. So now what we're going to do with the remaining, I'm going to give us, let's see how much we can do in 15 minutes, and that will leave like 10 minutes for questions. So we're going to go through and we're going to program parts of this. So depending on your manufacturer's software, you may have to program alarms. You may not have to program alarms. And some folks like to hard code their alarms in the actual programs. Some folks prefer to just have the points trigger alarms. It really just depends both on the specification as well as your personal preference. So we're not going to be coding any alarm conditions just due to time, but we will look at, okay, we've got this system, how do we go through? So the first thing we got to do is we have to identify our physical points and our logical points. So what I like to do is just kind of give a read through the sequence of operations. Okay, supply fan shall run, units commanded to run. All right, supply fan shall have these things. Okay, so we've got a supply fan. I'll highlight that. That's obviously going to give us, fan status. Why is this highlight? There we go. It's going to give us fan status and fan command. Okay, so we move along. Electric preheating stage. Okay, so we have a single stage of electric preheat. All right, so that's a point right there, right? Preheat command. We also have mixed air temp. Okay, so mixed air temp. We look, okay, we got outdoor air, and we just continue to go through this. Supply fan status, preheating stage, freeze protection, mixed air, supply fan status, cooling valve, zone temperature. Okay, so we see we got, you all are getting the point, right? I don't literally need to go through every point in here, do I? I don't think so. All right, so we see that we're able to figure out kind of all of the points that we need. So we figure out our physical points and our logical points. And then what I would normally do, but because we're working with a PDF, we're just going to go with it as we have it. But what I would normally do is I would actually kind of move the sequence chunks around. I would break these out into chunks and I would move them around. I would say, okay, well, this is run conditions. Obviously, everything's freaking dependent on the system turning on. So that would probably go towards the front. Supply fan also would go towards the front. Preheating, I would probably move towards the back. I would probably move cooling up towards the front, followed by heating valves. And I'd probably put economizer in front of both of those, just because it's a free cooling mode, things like that. Mixed air, CO2, those would all come afterwards. Return air, that's just saying, hey, we got some alarms. So all in all, not too bad of a thing to program. So first thing we need to do, right, is we're enabling this based on a time schedule. Okay, so, I could go and we could go to the kit and add a schedule and do all that fun stuff. but just for the sake of time, we're just going to call this aux schedule. Okay. If I can type, just called aux schedule because typing is apparently a challenge today. And we'll just, for giggles, we'll set this to true. Okay. All right, so looking at our schedule, okay, and then we have an occupied and a unoccupied command with cooling set points. So let's go through and start adding our points, right? So we're going to have a zn-t. Okay, zone temp. We are going to have a sf-s, supply fan status. We are going to have a mixed air temp. Okay, let's see what else we can find in here. We're going to have, oops, let's go back. Let's see what else we have. We have supply fan status. We have cooling valve. Okay, status, outdoor air temp. We got a return air temp. We got a mixed air temp. We got a CO2. Okay, so mixed air temp, supply fan, return air temp. We'll add that. Gosh darn freaking thing. I'm going to replace my mouse after this webinar. This is really frustrating. All right, here we go. So we'll continue, right? Schedule, zone temp, supply fan status, mixed air temp, return air temp. I know schedule is a logical point, but that's all good. Zone temp, supply fan, there, OAT. Okay. And I'm sure I missed something on here, but we'll get it when I come back. Gosh darn freaking, why are you doing this? All right, so we'll add that right here. Here we go, supply fan command. We'll add, actually, that should be a Boolean. So we'll just change this real quick. Cooling, oh. Like I said, we're doing this on the fly. We'll do a Boolean writable, supply fan command. We'll do a numeric writable, and we'll call this heating output. And we will do a Boolean writable for preheat command. Because remember, it's electric, so it is not, unless it specifies that it's like SCR, then it is going to be a Boolean command. It's going to be an on-off command, like with a rib UNC relay or an IDEC driving it. Okay, so we've got supply fan command, cooling, heating, preheat, and we are going to have our economizer. So OAD -O, and we're going to have our opposing RAD-O, right? So outdoor air damper and right there, return air damper, and like I said, I knew I would remember something that I missed. We're going to have return air CO2. And I believe that is all we have for our physical points. CO2, mixed air temp. I don't think we have a low temp sensor. I just think it's a oh, there we go, freeze stat. So we do have a low temp alarm. And that will be, my goodness, talk about being frustrated. It's always, that's a lesson for all of you. It is always the low-priced peripheral device that causes the problems. It's the bad sensor, it's the bad relay, or in my case, it's the bad mouse that needs to desperately be replaced. All right, so we've got all of our physical points here. Now we need to add some set points. Okay, so we are going to have a couple different points, right? Let's take a look at what we're working with. So we have our outdoor air enable set point. We have our zone temp set points. We're going to have our CO2 set point. Okay, so we're going to have a couple set points, and I'm sure we will add more as time goes on. So CO2 set point. Okay, we'll just kind of drag this guy down here. And what I'm going to do, just for the sake of time and your own personal sanity, is I'm not going to add every single set point and eat up all our time. I'm going to just go through some Boolean logic, and I'm going to add the set points for those. But realize in a program, you would typically not do that. You would take your time, you would add all of your set points, or as many as you can reasonably infer, and then you would go and do your Boolean logic, and then you would go and do your analog logic. But because we are 18 minutes left in the webinar, I am going to just do that. Okay, so let's start with fan command. We need this for pretty much everything. Supply fan shall run anytime it's commanded to run unless shut down with safeties. Okay, so we have a couple alarms and we have runtime exceeded. I am not going to go and program these just for the sake of time. So our supply fan is going to simply be driven by our occupancy schedule. Okay, pretty straightforward. Now, just so you know though, if we were driving on those conditions, we would use an AND block and we would say that all of those conditions are false, and or we could use nots and say all those conditions after notting them are true in order for our supply fan command to enable. Just depends on your own personal preference, how you like to read the programs. All right, so with that being said, let's look at right here. Okay, we've got a cooling set point and a heating set point. Let's look at cooling mode. I know I said we would do economizer mode first, but let's just look at cooling mode. Okay, so cooling controller shall modulate to zone temp. So we're going to have an unoct and an oct set point, and we're going to modulate it to control those. Those unoct and oct set points are 75 and 85. Alrighty, so we're going to need to have a select, and this is where I have to remember is Boolean select is driven off of, no, I don't want select. I actually want switch. And let me remember here if I'm going to use a Boolean switch or if I'm going to use, yeah, I'm going to use a numeric switch. That's right. So there we go. Okay. So what I'm going to do with my numeric switch here, and I'm going to label this as, let me go back here, rename. I'm going to label this cooling set point switch. Okay, and so my schedule is going to go here, and it's going to go into the switch input, right? And we see that it's true, and so when it's true, I want to have my cooling set point. Now, some folks will just straight up hard code this into the switch. The problem with doing that is, as we read the spec, it's got to be adjustable. And whenever you see adjustable, that usually 9 times out of 10 means from the UI, from the front end. And so because of that, right, because it has to be adjustable, we're going to have a occupied cooling set point. I'm just going to copy that. And let's just, right, let's copy paste. We're going to call this unoc cooling set point. And so those were, if I remember correctly, 75, 85. So let's set this. And we'll set this bad boy to 85. Okay, and we'll grab these logic blocks right here, drag them down a little bit to make some room. I personally don't like, if I can, putting my variables in the logic flow. I like to keep them all kind of stacked and organized. It's a little OCD thing, but you know, it works for me. So we'll go here, and this will go into true, this will go into false, and now we have 75 degrees is our set point, okay? So we've got our set point calculation, and we have to look at what is going to enable our cooling valve. So that will be our Boolean, okay? So our Boolean is gonna be our enable points right here, right? Cooling valve shall be enabled. Let me undo that. Cooling valve shall be enabled whenever outdoor air temp is greater than 60. Economizer is disabled or fully open, and the zone temperature is above cooling set point, the supply fan status is on, and the heating is not active. Now, obviously we have some logic here that we have not written, so we'll have to use a placeholder until we write it, and that logic, right, is right here. Heating is not active, and right here, Economizer is disabled. So since we haven't written Economizer control and we haven't written heating control yet, we are going to leave those as placeholders and we're going to come back to them. But outdoor air is greater than 60, okay? So, oops, close that. Here we go. So let's go to OAT, cooling, enable, set point, okay? And let's go to our comparators, which should be under logic. And we're going to say, what did it say again? It said OAT is greater than 60. Okay. So actions set 60. And we are going to say OAT right here. Our OAT coming in here is greater than 60. And once again, we're going to have to go kind of drag this stuff down a little bit. And what I'm not getting into here, folks, is that you can kind of nest programming inside folders to make this even cleaner. Like, I would not have everything on a single screen. I actually would have folders, and then I would link out of those folders. So I would have a cooling only folder. I would have a heating folder, and those would be under my program, and I would put my logic in there to kind of make it cleaner, but we're just doing it dirty here. So realize that in a production code, so in actual commercial code that you would be taking to your customers, you would want to make it a little bit cleaner, okay? And I realize that we are starting to rapidly approach our time limit. Okay, so we see we've got our first thing done. And usually what I will do is I will have this printed out and I'll put a check mark next to it when I've done it. And I will work my way down. And what I like to do, and this is a really cool tip that I really encourage you all to follow, is when you are programming according to an SOP, according to a sequence, and you have an AND block scenario, which this is obviously an AND block, right? And. And by the way, most sequences of operations are not going to be this clear for you. But when you have an obvious AND scenario, program according to the AND block. So your first thing into your AND block, okay? So first thing into the AND block should be this right here, because now as I'm reading the sequence after the fact, outside air temperature is greater than 60 degrees. Oh, look, there it is, the first input to my AND block. Now we say economizer is present. We don't have that yet, so we're going to skip that, right? And we're going to just pin our slots. Okay, and we're going to say, and the zone temperature is above cooling set point. Okay, so we've got our outdoor air temp, and we've got our set point right here. And we're going to grab, and you're seeing how this greater than this comparative design pattern is being used, right? So I'm going to grab this, copy and paste it. And in this case, if I really wanted to, I could say ZNT dash greater than or zone set point. Okay. And then right here, I could say, I could rename this bad boy to be OAT. What is it? Let me look at it one more time. Yeah, OAT greater than cooling enable set point. You seeing how we're doing this right here? Okay, so you've got that kind of describes what we're doing. That kind of describes what we're doing. We're saying zone temp. Okay, so let's find zone temp on here somewhere. And let's set it to 80, just for the hell of it. All right, and then let's grab our calculated set point. And that is going to go to input C. Okay, so we're seeing, once again, following our programming. Now, you won't in every manufacturer's software be able to rename your logic blocks, but if you can, I recommend it. And I'm going to say cooling enable 1 because I'm going to need a second AND block because we have 5 conditions. So then we say supply fan status is on, right? So let's just set this to true. Why did I do a numeric for supply fan status? Let's grab that real quick. Okay, put that bad boy right there. Set, true, okay. And then we're going to output this into right here. And then, we continue. We have our heating, which we don't have yet, which would be in a second AND block. And then all of that, right? All of this right here, let's drag this over here, would go and it would enable our PID loop. So we'll call this cooling PID. So this would be our Boolean logic. We've written our Boolean logic. Now we can write our analog logic, which is our cooling PID loop. So we go here, pin slots, control variables, set point, loop enable. Okay. And we would output this. Gosh darn it. Output this to loop enable. And now our loop's enabled. And then our cooling PID. Cooling valve is going to measure zone temp and modulate it to effectively control to the cooling set point. So we have our cooling set point right here coming into there, and we have our zone temp going into our controlled variable. And then we would set up our PID loop. We would set up the actual P band and I band and direct acting versus reverse acting. And then we would go and set that right into our cooling output and drive our cooling output. So there you have it. That is how, and I realize we are 5 minutes over my target time of 11:50 to finish this, but that's how I read through the sequence and I write that snippet. Now, as I mentioned, right, I would put this in a folder. I'd have cooling control. And I would put all this code in there. And then as I did that, I would pin my outputs, or I would link, sorry, not pin, I would link to specific things within that logic. And I would then have it all sitting in there. So it's not this garbled mess. But with the time we have, that's just, we didn't get to that. All right, so we still have 5 minutes, and I really wanted to make sure that I took some time to answer any questions. I know, unfortunately, we didn't get through as much of the program as I wanted us to, just because of the time constraints. But I did want to stick to the hour that you all had committed to be here. So with whatever questions you have, please type them into the questions box.